Okay. How's everybody doing? Good weekend?
Good.
Okay, so we're gonna move a little bit away from, well, we're gonna show one of the applications of refraction. That is the one that probably you are more familiar, and it's basically working with lenses. Every lens, the way you can think of it is that it's just a geometrical shape, it's just just a geometrical shape in which you have refraction on both sides of the lens. So did you imagine a lens kind of like this? You're gonna have rays of light going into one side, kind of like a prism, and you're gonna have refraction on one end, and you're gonna have refraction on the other end. Okay, and if the conditions are correct, you create an image. So what I have here is just a light source that is gonna have it has a target on it. I cannot say it, but it's a little target, just an arrow and a cross sight. And over here, I have a lens. And we're going to talk about a little more about the different kind of lenses that are there. Okay. And it's just a regular lens. So what I'm going to try to do is to change the lens and then show the lens, the image on the wall. And let's see, I need to be dark. You can see on the wall, it's kind of like a blurry image. So I'm gonna try to move this. Kind of like that. You can see the kind of like the image a little bit of kind of like the arrow. So let me move this arrow. There you go. Okay, everybody can see it? Okay, so this is something very simple. You have light coming from this lamp. You have the screen with some drawing on it, and the light is being captured by the lens. And then the rays of light are gonna change. They're gonna be refracted, and eventually they're gonna converge in a single point, and that point is gonna be on the wall. Okay, and they create an image. Now, this image is kind of interesting. I know it doesn't look like that. So what I'm gonna do is I'm gonna block the light. I'm just gonna pass my pen through it. And I'm gonna move it from the top of the image, from the top of the object, sorry, to the bottom. So I'm gonna move it up and down. And just look at the shadow of the pen. Yeah, so I'm moving up and down, but the shadow goes down, up. Okay, so I'm gonna try to do it again. So I'm moving from up, down, and the shadow appears from the bottom and starts moving up. Okay, so it means that we call this an inverted image. So the arrow here is pointing up, but the image is gonna be pointing down. Okay, so we call that an inverted image. Now, all of you can see that image. The image is being projected on a wall, and it doesn't matter where you guys are in the room, you can still see that, that image. So when something like this happens, we call it a real image. Andrea, you've fallen asleep.
Yeah.
Yeah. And you with your eyes closed.
I was reaching my eye.
I can, you're on the front row, I can see you. So we call that a real image, and it's basically an image that everybody can see, regardless of where you are in a room, okay? It's an image that physically exists, and it can be projected on the screen. Something like the projector here in the room, or when you go to the movies and you have a screen projected on your movies. Those are examples of real images. Okay. There are other kind of images that lenses can create, and they are called virtual images. And virtual images are images that can only be seen by one person at a time. And they're kind of difficult. Everybody has seen virtual images. Come in. Oh, hello. Visual images are a little bit more difficult to show because the only way you can see them is if you are in front of the lens. But for example, when you use a microscope and you put your eye on the eyepiece, and you can see that you need to position your eye in the right place, otherwise you have a shadow because of the eyepiece. Those are virtual images. That's an image that's not being projected on a screen. You cannot put a screen and see that image. You have to see it. People that use glasses, all the glasses that they create virtual images. Any optical instrument, anything that you put on your eyes are going to be creating a virtual image. So what we're going to try to do on this week is try to work of when do we have virtual images, when do we have real images, and how can we calculate the size and characteristics of the images created by one or multiple lenses. Okay, one of the things is that if I move this setup, well, now you're going to see that yes, the image is a little bit larger, but it's also a little bit blurry. So I need to move my lens again. And I can move it again until it's again on focus. Okay, so that play of how far the image is going to be compared to the size of my lens and the distance of the lens to the object, that's what we're going to try to do. Okay, make sense? Okay, so I'm going to turn this off. Yep, that's on. Bless you. Oh, cool. Okay, so this is thin lenses. Okay, so a lens basically what it's going to try to do is to focus the light from an object and to create an image. So we use lenses to create images. They work by refraction. And we can create image to magnify or demagnify and create images for magnification or demagnification. So images. the magnify. Well, I guess cannot. Okay. Okay. Now there are different kind of lenses. What we're going to be talking about are specifically with thin lenses. So a thin lens is a lens where the thickness is not going to be can be ignored with respect of the other dimensions of the lens. And one of the things that we care about the thin lenses when working with the thin lenses is their shape and what we call the focal length. Okay, so first I'm going to show the shape, and then we're going to be talking about and then we talk about the focal length. Of course, I forgot to share this thing. Okay, there are a lot of shapes on working with lenses. The ones that are more common, bless you, are lenses that are usually part of a sphere. So you can imagine that if you have a sphere and you cut a part of the sphere, then the area that you cut this is going to be your lens. Okay. This particular shape, we call this a plano convex lens. We can also have biconvex lenses. This is a plano convex and a biconvex lens. Would be something like this. We also have plano concave, in which we have a flat surface. And then we have a curve on the inside. And we can have biconcave lenses. Okay, plano convex and biconvex lenses, sometimes they're referred as positive lenses. And plano concave and biconcave sometimes are referred as negative lenses. Okay, so there are more shapes. There are cylindrical lenses. Cylindrical lenses, I don't know if I can draw it, but kind of look like this. So it's only have a curve on one axis. So this will be a cylindrical lens. Cylindrical lenses. And you have a spherical lenses also. In which the profile of the lens is not made by a sphere, but it's made by something else. It can be an ellipse or a toroid or something. So it can be more like a parabola. These are more difficult to draw. And there's something that's called free-form optics, free-form lenses, in which you can imagine that the shape is kind of arbitrary. Oops, I definitely cannot draw this. Yeah, but you can, yeah. Yeah, so the shape is not even a sphere or cylinder or an ellipse. It's just something completely different. It's just a polynomial. Okay. Obviously, for the class, we're not going to be talking about a spherical, cylindrical, or even and freeform. The ones that we probably going to be using are just these lenses. And because we're only working with thin lenses, it really doesn't make any difference if you're working with planar convex or biconvex or planar concave or biconcave. The shape matters if you are working with thick lenses, but if it's a thin lens, it really doesn't matter. So for the class, we're only going to be assuming biconvex and biconcave. Okay. Now, usually when I draw or what is common is that when you are working with biconcave lenses, biconvex, sorry. So you have something like this. To draw it a little bit faster, you do an arrow, well, double arrow like that. So this will be a biconcave lens. And a biconvex will be something like that. Okay, it's just symbols that we use to talk about these kind of lenses instead of drawing the whole thing. Okay, and this line is where the refraction happens. So this is where the point where the refraction is gonna, we assume that the refraction is gonna happen. Oh, it's the other way around? I was looking at your face that you were very confused.
Yeah, that happens a lot.
Biconvex, biconcave. Yes. Better. Okay. Okay, makes sense? Okay. So now we're gonna be, so those are the shapes that we have of lenses. Okay, those are the general shapes that we're gonna have. So now we're gonna be talking about the focal length and what is the focal length and why is that we call a particular kind of lenses positive lenses and some of them are negative lenses. So when you're working with an optical system, and we have done this in the past, one of the things that you need to do is to set up your frame of reference. And that set of reference, when you work with optics, one of the main axes that you're going to have is the optical axis. And we use the optical axis to put every single optical element along that axis. So here I'm gonna have my optical axis. Okay, I'm gonna put a lens here. And this lens is gonna be a biconvex lens. Okay, now somewhere along that optical axis, I'm gonna put a light source. And that light source, I'm gonna assume that is really, really, really far away. Now, when you have light sources, you can imagine that light kind of diverges from that light source. But if the light source is really far away, you can assume that all the rays coming from that light source are parallel to the optical axis. So all my rays, all my light coming from the optical axis is going to be incident into my lens. Okay, and one of the things that lens or a positive biconvex lens is going to do is that it's going to focus all the light into a single point. Okay, so if your lights are parallel to the optical axis, what the lens is going to do is that it's going to focus all the beams, all the rays into a single point. Okay, and when all the rays are converging in a single point, we say that that light is being focused. Okay, and the distance from the lens to the focus point, so this distance, that's the focal length. So if I say that a lens has a focal length of 10 centimeters, it means that the light is going to converge at 10 centimeters. If I say that a lens has a focal length of 2 meters, it means that all the light is going to converge in 2 meters. Okay. You can more or less get an idea of the focal length of the lens just by looking at it. The more curved it is, the shorter the focal length you're gonna have. The more flat, you're gonna have a really, really long focal length. Okay, yes?
Does that go for concave too?
For concave, it's a little bit different. Okay, so we call biconvex length positive focal length because we assume that the focal length is always going to be positive. It's always going to be larger than 0. So in a convex lens, the focal length is always going to be larger than 0. Don't go.
Welcome back.
Promise? Well, she got her stuff. Okay, now for the negative lens, we're going to do the same thing. We're going to have an optical axis. And I'm going to have the same light source, same position, same characteristics. So I'm still going to have all my rays parallel to the optical axis. Okay, and when light hits, a light that is coming parallel to the optical axis hits a concave lens, light is going to spread out, it's going to diverge. So light is just going to diverge. Okay, if I were to trace these lines that are diverging, if I were to trace them back kind of like a straight line, I will see that they appear to come from a single point. So that's the focal length of the concave lens. So because the focal length is behind the lens, we call that a negative focal length. That's why we call them a negative lens. So concave lenses has a focal length less than 0. Okay, now, so if I have a biconvex lens and I have light coming from left to right, you can imagine that, well, all the light is going to be focused on one single point. Okay, and that's going to be my focal length. Okay, I can switch. I can flip my lens, and it wouldn't matter. The focal length will be the same. Or I can have my light coming from right to left on the opposite direction, and if it's parallel, the thing is going to happen. The same thing is going to happen. I'm going to have light being focused at the same distance, just in the opposite direction. Okay, so a lens, every lens have basically two focal points, one to the left and one to the right, and they're going to be symmetric with respect of the lens. Christina, make sense? Okay, now most of the time light is not going to be parallel to the optical axis. Most of the times light is going to come from random places. And one of the things that we want to do is to calculate or to create images with the lens. Okay, so I'm going to do a simple example of how you calculate where the image comes from. So again, I'm going to have an optical axis. I need a ruler this time. These things are so old. Okay. I didn't do that. Anyway, so I'm going to have my optical axis, I'm gonna have biconvex lens, and I'm gonna say that the focal length is gonna be right here. That's gonna be my focal point. Okay, so I'm gonna have two focal points, one in front of the lens. I'm gonna have another focal point behind two. So I'm gonna have here my focal point. Okay, and here's one of the parts where optics becomes a little bit complicated. The optical axis is gonna set up a frame of reference, and everything above the optical axis is gonna be positive. It's gonna be positive distances. Anything below the optical axis are gonna be negative distances. Okay. The other origin is gonna be where my lens is gonna be. Okay, and from the lens, the whole optical system can be divided in object space to the left and image space to the right. Okay, and I'm gonna assume that all the objects are always gonna be to the left, and I'm gonna assume that the images are gonna be formed to the right. Okay, now I'm gonna have two different frame of references when I'm talking about images and when I'm talking about objects. Okay, so when I talk about an object, positive distances are going to be to the left. To the left of the lens. And negative distance are going to be to the right of the lens. And for the image, it's going to be the opposite. Positive distances to the right of the lens. Negative distance to the left. Okay, so let's say that here on this space, I'm gonna have an object, and I'm gonna say that the object is 10 centimeters. So because I'm telling you it's 10 centimeters and that's a positive distance, it means that it's gonna be from the optical axis, gonna be up. Okay, and I'm gonna put this object somewhere around here. If I were to say that the object has a height of -10, even though -10 for height doesn't make sense, in this context, it means that it will be below the optical axis. Okay, so this technique to calculate where the image is going to be formed was developed by the Greeks. It's basically based on geometry, but we still use it. Like basically every single software that we use for optical design is based on this technique. Like this is what I do pretty much for a living, is just work with lenses and design them, and we use an optical simulation that is based on rays and stuff. So for every single point in the on the object, we're gonna assume that they're gonna be a bunch of rays coming out of that object, and some of those rays are gonna be captured by the lens. Okay, Because we can, in theory, have an infinite number of rays, we're going to limit that number of rays to only 3. And those 3 are called the principal rays. And the principal rays, I'm going to assume at this point that are just going to come from the top of my object. So my optical ray, my principal rays are going to come from this point. And they're going to be 3. One of them is going to go parallel to the optical axis. So it's going to go like this. And it's going to go parallel to the optical axis all the way to the lens. Now, we know that when light goes parallel to the optical axis, hits the lens, it's going to go and it's going to focus on the focal point. So this ray is going to go and pass through the focal point. So I'm going to do it. And it's just going to continue all the way like that. My second principal ray is going to go from my from the same point in my object, and it's going to go through the center of the lens. So it's going to go from the top to the center. Okay, and that ray just keep going straight. It doesn't get refracted of any kind. It's just going straight. So this guy just gonna keep going straight. Okay, and the third principal ray is gonna go through the focal point on the object space. So it's gonna go from here all the way to the lens. I make my drawing, I did my object very too tall, but you can imagine that the lens is big enough that it will capture that lens, and then that ray will come out parallel to the optical axis. Okay, now you can see that somewhere far away, these 3 beams are gonna converge. And when they converge is when they create the image. So over here, we're gonna have an image of my object. And that image is gonna be flipped, is gonna be upside down. Okay. So when you have an image on the image space and it's flipped with respect of the object, we call this a real image. Okay, there are 2 dimensions that I care, and that's basically going to be the distance from the object to the lens. I'm going to call this of all. Okay, And then I'm gonna have the distance to the image, which is gonna be from the lens to the image, and that's gonna be d sub I. Okay, there is a very simple way to calculate where the image is going to be created given the focal length of a lens and the distance to the object. And that's basically what we call the thin lens equation. And that's, I think, is the fourth equation of the whole section. And it's basically that the inverse of the focal point or the focal length is going to be the sum of the inverse of distance to the object plus the distance to the image. Yeah, that's not a negative. That's just a smudge on the screen. Yes.
So what is F in this equation?
F is the focal length of the point of the lens. Cameron?
I was gonna ask, can you like show the drawing that you have? See where F is going.
F is the focal length of the lens. Okay, and the focal length of the lens is going to be the same as the distance from the lens to the focal point. Okay. Now, I'm going to use this equation, and I'm going to say that I want to calculate where the image is formed if I have a 20 centimeter focal length lens, and the distance to the object and the object is placed at 50 centimeters from the lens, from to the right of to the left of the lens. Okay. So I have my lens, my focal point. This will be 20 centimeters. And my object is 50 centimeters to the left. So it's going to be something like this. So I want to know where my image is formed. Okay, so I'm going to use the thin lens equation. Okay, and I want to solve for d sub I. Okay, so I'm gonna do a little bit of math over here. So I'm gonna have that 1 over d sub I. It's gonna be 1 over f minus 1 over d sub O. I'm gonna try to simplify this. So I'm gonna have f d sub O minus f. And I'm gonna invert all these things. So d sub I will be f dO over dO minus F. Yeah. And once I have that equation, I can substitute values. You can, I'm gonna be working on, as long as all these units are consistent, you can work in centimeters or meters. I'm gonna do it in meters. So my focal length is gonna be 20 centimeters. So that's gonna be 0.2 meters. Distance to the object is 50 centimeters, so that will be 0.5. And over here, I'm gonna have 0.5 minus 0.2. So if someone can give, I don't have my calculator, so if someone can give me that result.
It's 0.3 repeated.
Say it again.
It's 0.33.
0.33. 0.33 meters. Okay, so here's the thing. We end up with a distance to the image, with a positive distance to the image. And remember, positive distance to the image are gonna be positive to the right of the lens. So the image is gonna be 33 centimeters from the lens, from the right to the lens. And it's gonna be inverted. Okay, so this distance is gonna be 33.3 centimeters. I can calculate how big is the image with respect of the object. So I want to calculate the magnification of the lens or the magnification of the image. And that magnification is gonna be negative d sub I over d sub all. So in this case will be negative 0.33 over 0.5. So I'm gonna end up with a magnification less than 1. So the image is gonna be a little bit smaller than the object. Yeah, and that negative sign is just gonna indicate that it's flipped. Yeah, makes sense? Okay, so let's say that I have exactly the same thing. So I have a focal length of 20 centimeters. But now my distance to the object is 15 centimeters. So now my object is gonna be somewhere around there. Okay, and I want to calculate what is the image. So use Thinless equation. And calculate what is that image. Cameron, what you got?
I got -60.
Okay. What do you mean you don't know? You got -60?
Yeah.
So I'm gonna have FDO. F. Yeah, everybody got something like that? Okay, so now we got a negative distance, and the math is okay. We can see that here in the denominator we have 0.15 minus 0.2, so that's gonna give me a negative value. So yes, I'm gonna end up with a negative distance. Now, the negative distance for images are gonna be to the left of the lens. So that means that that image is being formed somewhere over here. Okay, I can calculate the magnification. And the magnification is negative di over do. So in this case will be negative. Di is negative 60. And do is 50. So this will be what, 1.2? Negative 1.2? Or positive 1.2? Or something like that. So now the magnification is positive, which means that the image is not inverted and it's going to be pointing in the same direction as the object. Now, when you have an image being formed on the object space and is not inverted, this is what we call a virtual image. Okay, this image cannot be projected on a screen. So it doesn't matter if you put a screen over here or anywhere, you cannot look and you cannot see that image. The only way that you can see that image is if you put your eye somewhere along the optical axis. You need to see through the lens and then you can see this image. That's basically what happens when you're using a microscope. You need to see through the lens to be able to see that image. So this is an example of virtual image. So virtual images they are created they are going to be created in the object space. So the distance to the image is going to be less than 0. They are not going to be inverted. So the magnification is going to be positive. Okay. Now, last exercise really quick. Does it make sense? Virtual images are kind of tricky because it's like, what do you mean we cannot see it? So what's the point? Well, yes, you can see it, but it's not something that you can project on a screen. So the last example is working with negative lenses. So let's say that I'm going to have a negative lens. Now, on a negative lens, the focal length of a negative lens is obviously going to be negative. So let's say that I'm going to have a negative focal length. I don't care what it's going to be. I'm going to have focal points in front and behind the lens, and I'm going to have an object. And I'm going to create an image, and I want to find out what is that image. So I'm going to do the thinness equation. So I'm going to have that 1 over the focal length is going to be 1 over DO, 1 minus plus 1 over DI. So exactly same equation. Solving for the distance to the image. Minus F. Okay, and now I'm gonna try to find out what is that image, just in terms of this value. So I'm gonna have negative the focal length times DO over DO minus the focal length. So this will be negative FL times DO over DO plus the focal length. Okay, so one of the things that we always assume when we're working with lenses is that the object is going to be to the left of the lens. So the distance to the object is always going to be positive. So it means that this denominator is always going to be positive when we're working with negative lenses. Okay, but the numerator is always going to be negative. It doesn't matter where you put the object, is you put it before or after the lens, the focal point, you're always going to have a negative distance to the image. So negative lenses always produce virtual images. Okay, it doesn't matter where you put that lens, where you put that object, it always going to produce a virtual image. When you work with positive lenses, where you place your object matters. We're almost done, Cameron, just 5 more minutes. So if the object is smaller than the focal point, you create a virtual image. If the distance to the object is larger than the focal point, you're going to have real images. Okay? Make sense? We'll do a couple more problems on Wednesday and Friday. But I hope this makes sense. Okay, have a good day. See you guys on Wednesday.